Modern machine learning models navigate massive, complex systems of variables to find the absolute lowest point of error. To do this efficiently, they must calculate exactly which direction leads down. Differentiation provides the mathematical framework for mapping these systems. It is the process of finding the rate of change of a function with respect to a specific variable, revealing exactly how a function's output shifts when its input changes. This equation is the formal mathematical definition of the derivative. It specifies how an output responds to an infinitely small change in input, represented here by h approaching 0. This formula serves as the mechanical engine for measuring instantaneous change at a specific moment in time. Software algorithms use this precise measurement to continuously update and adapt. These are known as gradient-based algorithms. A gradient-based algorithm is a computational method that uses the derivative of a function to find its minimum or maximum value. Constructing a formal mathematical model of instantaneous change is a mandatory prerequisite for building algorithms that learn. Without a reliable way to measure how a system is shifting, a computer cannot optimize multivariable systems. This graph shows the quadratic function f of x equals x squared. A secant line intersects at points x and x plus h. As the gap between them shrinks to 0, the secant line resolves into a tangent line, and the resulting derivative is 2x. The derivative represents the numerical slope of this exact tangent line. Taking a rough average between two distant points only provides an estimate of a trend. The tangent line isolates the precise trajectory of the curve at an exact, frozen moment. Calculating this instantaneous trajectory allows computers to determine exact directional vectors, pinpointing the specific path a function is taking. Manually calculating the geometric limit as h approaches 0 is highly inefficient. To compute rates of change rapidly, software engineers use a systematic algebraic toolkit. This layout displays the basic building blocks for polynomials. The power rule dictates the derivative of x to the power of n is n times x to the n minus 1. The constant rule establishes that the derivative of any fixed constant is 0. For larger equations, the sum rule differentiates sequentially. For multiplied functions, the product rule uses a cross-multiplication pattern. The first's derivative times the second, plus the first times the second's derivative. For divided functions, the quotient rule provides the structural formula. Balancing these larger equations introduces room for human error. Common points of failure often stem from simple algebraic simplification mistakes when combining these terms. These algebraic rules translate geometric concepts into direct, programmable, and highly efficient code that machines can execute millions of times per second. Basic algebraic rules have limitations. They cannot differentiate complex composite functions, where one function is nested completely inside another. The chain rule peels back layers. Consider f of x equals x squared plus 1 to the third power. We differentiate the outer exponent shell first, yielding 3 times the quantity squared. Then we differentiate the inner polynomial, resulting in 2x, and multiply it against the outer result. Forgetting the chain rule is one of the most frequent and catastrophic errors in applied calculus. Composite functions are the mathematical backbone of layered computing architectures. Deep neural networks, which stack mathematical operations inside one another, require the chain rule to train and optimize. A deep neural network is an artificial intelligence architecture inspired by the human brain that processes data through massive arrays of interconnected nodes. We can push this logic further by iterating the process, taking the derivative of a derivative. This vertical stack illustrates the second-order derivative, measuring how fast the first derivative changes. By mapping the relationship, slope values match up vertically. The second derivative identifies curvature. Its positive or negative values map directly to the concavity of the original base function. Measuring this curvature allows mathematicians to conclusively identify whether a flat slope on a graph is a local maximum peak or a minimum valley. Identifying these mathematical minimums through concatenity is how physics engines and machine learning loss functions verify stability. A loss function is an algorithm that measures how far an artificial intelligence model's predictions deviate from the true values. Two-dimensional, single-variable functions build foundational logic, but modern data science involves massive systems with millions of independent variables. When a function has more than one variable, we apply partial differentiation. This three-dimensional surface plot represents the multivariable function f of x and y equals x squared y plus y cubed. Partial differentiation isolates variables by freezing the others as constants. Treating y as a constant slices the 3D surface, isolating a 2D curve for x, yielding 2xy. Conversely, treating x as a constant isolates a perpendicular curve for y, yielding x squared plus 3y squared. It is essential to distinguish partial derivative notation from ordinary derivatives, as they imply different behaviors. This visual matrix summarizes three core spatial models. The first derivative provides slope, the second reveals curvature, and the partial derivative scales into multivariable dimensions. Partial derivatives are the tools used to build gradient descent algorithms. They allow computers to calculate downward vectors for millions of variables simultaneously. Mastering multidimensional change and avoiding algebraic pitfalls allows engineers to calculate the precise weight updates required to train deep neural networks.